Okay, so what is our goal? Our goal is understanding how you go out and you capture energy from sunlight and you use it to do what you want to do, which is pretty much anything but waste heat. You want to be able to store that energy in chemical bonds, you want to use it for solar cells, and you just want to grab the energy from the photon and hold on to it. The technique shown doesn't work at all, but you can do this. Trust me, it can be done. But that's the idea. And what's it mean? Well, if you're going to do this type of very sensitive spectroscopy, you need a very well-controlled laboratory environment. You need the ability to dictate the temperature and have it be really stable. So about 0.1 degrees is workable. 0.05 is better. 0.2 is about what I had as a postdoc, and that's marginal, but you'll get by. Anything less than 0.2 over the course of a few days, and forget it. And people have to be able to come in and out of that space. Lasers have to be able to turn on and off. You have to have people working on things, and you've got to be able to hold that 1/10 of a degree. Now, holding 2 degrees, I mean, my living room does that. That's not so hard. Holding 1 degree, that's sort of like what my office does, and in fact, the 400,000 square foot building that I work in can hold a degree. But getting down to 1/10 or less in an actively used space with a kilowatt of load plus people, and some graduate students are brighter than others, but they're all worth about 100 watts a piece when you get down to it. I have a dim bulb joke too, but we're not going to go there. Anyway, so what do I need in a space like this? We need about 1/10 of a degree Fahrenheit. We need about 0.5% of relative humidity. We also are very sensitive to vibration. I mean, I have a table, it's a 6,000-pound table. It floats on a bed of nitrogen. It's pretty vibrationally isolated. The space itself will do about VCD. So it's decent vibrational space, but not spectacular. If I go to the sub-basement where some of my colleagues are, it exceeds NIST A. But it's a pretty good space. It's a pretty quiet space. We keep ourselves around 40 or 50 dBA, and it goes up a little bit when you start measuring dBc, but it's not too bad. So we've been able to do that. We have clean room HEPA filtering. My students don't gown up. It's not a clean room. That's about productivity. If every time they have to go from their desk to the lab, they've got to put on a gown, I lose productivity. So we sacrifice a bit there, but it's a low dust environment. It could be operated as a clean room. So this was sort of the baseline, and I was able to tell people what we needed. I was able to say to the University of Chicago and these guys that this is what we have to deliver. I don't really care what the temperature is, but it's got to be stable. I don't really care what the humidity is, but it's got to be below 45% where my hygroscopic crystals get ruined, and it's got to be stable. How do we do that? And there are a lot of design decisions that go into this. So the temperature, not so bad. 70 is good. You don't want an uncomfortable lab. So that one's pretty easy. Humidity, do you want to try and lock it at 45%? Do you want to try and lock it at 30%? Chicago's a rough place to do this. When I was in Berkeley, California, and it was always 15 to 18% humidity outside, it was pretty easy to think about what's going to happen, except the month of December where it rains, which means you take off and go to the coffee shop or whatever libation you might prefer. But in Chicago, we have things like summer and winter, which California doesn't really have. And that makes it a much harsher decision. So we ended up setting the lab around 35%. Based on the capabilities of the low temp water in the building and some reheating and energy sustainability issues. So we picked about 35% humidity with plus or minus about 0.25% to give us the control band, and that was the goal. And in fact, those are 3 of my students working on one of the lasers in the lab.